So we've defined our vertices as well as our edges. And the next thing we're going to do is we are going to write the actual search algorithm. In doing that, we want to recall that the depth first search algorithm is known that way because we will make a decision at each point to go as deeply as possible. Meaning, we're going to start at this node and we're going to go to the Bob node, and then our next decision would be to go deeper to the Dan node. And at this point, we can't go any further and we will backtrack. So we will go to the Bob node and then we would backtrack to the Abe node, and then we go rightwards. We go to the Cass node and we can go as deep as possible to the Eve node, and then we backtrack to the Cass node, and then we go as deep as possible, which is to the Flow node, and then we go back to the Cass node, and then we go back to the Abe node. So this is the path we are going to travel. Good. Now let's go write the algorithm. In writing this algorithm, what we're going to do is to make sure we are traveling along the right path. When we get to a particular node and can't go any further, we will print something. Okay, for instance, the first thing that's going to be printed is done, because at this point we have to start backtracking. Okay, and then we will print out Bob, and then we will go to Abe but not print it out, since we still have nodes to process before we finally come back to Abe. So we will go to Cass, Eve, print out Eve because we have to return. Go to Flow, print out Flow, and then we can print out Cass and then Abe. Good. So here's our algorithm. We are going to call it DFS, depth first search, and it's going to take some vertex. And we're going to check whether that vertex has a left child. And if that's the case, we are going to go along the left child and call the depth first search algorithm. Well, we could do that. Another way we could do it is we could check whether this vertex is a proper vertex or whether it is none, okay? And in that case, we know that we need to backtrack if it's none. If it's a proper vertex, then we can do a depth first search on its child. And if we can't go left any further, we can go right, or we can try and see whether we can go right. Now, once we have gone to the limit which is at the edge, then we can process a particular node. And at this point, what we will do is just print out the value of the node. Good. And now we can test our algorithm by calling it on the root node. or the root vertex. We run it and we see that it prints out Dan, Bob, Eve, Flo, Cass, Abe. So if we compare this sequence with what we have in our PowerPoint slide, then we notice that the first thing that gets printed out is Dan, okay, and then Bob, and then Cass, Eve, Flo, and then good. Now, if we want to get a more specific picture of these paths being followed, let's put some timing information, okay? Now, what we're going to do is we're going to start at time step 1, and each time we move along an edge, we want to increase the time step by 1. So the time step would be 2 when we get to Bob, 3 when we get to Dan, and we will also increase the time step to 4 when we are leaving this node, so that we will go to 5, and then 6, and then 7, and then 8, and then 9, 10, 11, 12, 13, 14. Good. So we are going to implement this time step information. And to implement the time step information, what we're going to do is let's set the time. We actually could use the timer. We could use the system time and this would still work. But it's much easier if we set our time. Let's say t is equal to 1 and then increment by 1. Okay. We would increment by 1 whenever we visit a particular node. And before we leave the node. Okay. But now this time information is not being held anywhere. We could keep the time information within the vertices. And to do that, let's let's hold them in attributes. We're going to say self.d and self.f. Now, self.d will be the time at which we first encounter the node, and self.f would be the final time for that node, the time when we last encounter it. Okay? So that's what we're going to do here. And then once we're leaving the node, we set it to this final time. Okay. Now we're going to set t to 0 at the start. And because this is a function in Python, this value of t is different from this value of t that is outside of the function. Okay. And to make them the same, or to make them refer to the same storage location, we're going to say global t. So now the t within this function as well as the t outside, they refer to the same location. And that means If we update t, we update this one global value of t, and that increment remains even when we get out of the function. Okay, good. Now to see what's happening, we could do, let's create a list of our nodes, okay? And we're going to call the list vertexes. And it's going to contain all the nodes. Now that we have our vertex list, we can step through each of these list items and print out when we first visited that particular list item and when we last visited the item. And we are going to write a for loop that does that. Okay, let's run that. Okay, there's a syntax error here. Now, if I get to this error, I know it says end of line while running scanning string literal. That pretty much means I have an opening parenthesis or opening double quotes without a closing corresponding double quote. Now, there seems to be another error. We want to do all of these, perhaps except for global T. Within the if statement. Okay. Let me execute this. Yeah, it does not. It has a D. So let me clear and execute. Okay, the visits are twelve. Okay, good. Now, when we're backtracking, you'd see we go from Dan to Bob, but then we did not put a number beside Abe at that point. So there's no 6 here. The reason is at this point, what we are actually doing is we are calling DFS vertex dot write child. Okay, so the point at which we update this f value is when we can't move any further, meaning we've gone as leftmost as possible and as rightmost as possible, and that's when we would print and update the time information for the finish time. Okay. Now, if we are at a particular node and we haven't gone down the right side, that means all we've done at that point is we might have made several calls to DFS left, and we have to do these calls before we get to print anything. or update the time for that particular node. Good.